So we have seen in the previous class some examples of Newton's laws, how to apply Newton's laws to understand the dynamics of bodies, right? So I've got one more problem of the similar kind, but a bit different kind of problem than what we have solved in the previous classes. All right. So the question is this: a boy of mass 58 kg jumps with a horizontal velocity of 3 meter per second onto a stationary skateboard of mass 2 kg. All right. So what is his velocity as he moves off on the skateboard? First thing would be to imagine this scenario. So a boy of 58 kgs comes with a velocity of 3 meter per second. He's walking. That's a walking speed, isn't it? No. 1 second. I got it wrong. 3 meter per second would be a running speed, isn't it? 3 meters per second would be a running speed. And he comes running and he gets on the skateboard, which is of 2 kg. And the question is, what is the velocity of the skateboard plus the boy? Can you imagine this? If a boy is moving at 3 meter per second and he weighs 58 kgs and he gets on a skating board, what would be the velocity of the boy along with the skateboard? Would it be more than 3 meter per second, or would it be less than 3 meter per second? That's the question that we are first need to think about, and then begin the problem and see if our intuition was correct in the first place. All right. So what do you think? Is the final speed going to be less than the initial speed? Right. So if skating board seems to be a little bit small for you, imagine a bigger object. A platform with wheels, maybe a platform with wheels, and you come running and get on this platform with wheels, a bigger platform with wheels. All right. Now, would it move once you get on the platform? Would it move with the same velocity, or with a greater velocity, or with a smaller velocity than your own velocity? Right? Once you've got the imagination for this, then we can go ahead and discover why exactly is that your intuition is correct. We all have intuition about these things, right? When we go about on the street, we do not really apply Newton's laws. We do not really use projectile motion equations, but we get it intuitively, right? So that's what is important for us. We have observed the nature enough that we've already got the intuition as to what is going to happen, right? So physics is basically writing that intuition down in terms of neat mathematical formulation, right? So Newton, when he says, okay, I'm going to give you 3 laws, doesn't really mean that, okay, henceforth this is how nature is going to work. Nature was already going on like that. Nature was already working in its own ways, and Newton is just a discoverer of the principles of nature. All right, that's what we do in physics. We discover things, we discover ideas in nature. We observe carefully and get ideas as to the working of the nature, and then we apply it to something else. Then we design things like a bicycle, maybe. Okay, look at the working of the bicycle, how complex it is, right? If you look at the gear cycle, how does a gear cycle work, right? All of that has to do something with Newton's laws. All right. So if possible, I'm going to give an example of how gear cycles might work, okay, on Newton's ideas. Not exactly the gear cycle, that would be a little bit advanced, but something that is related to gears and all those things. All right. And if you remember the buses, even the old buses, when they apply brakes, look at that. A bus is a big object. It's a massive object moving with speeds like 60 km per hour. And it's not possible for a man to physically stop the bus. But when the bus driver applies the brakes, how is it that his leg strength is enough to stop a big bus like that? All right. Now you might say, okay, there are electronic brakes and ABS system and all those things. Even before these things came into existence, before these things were invented, buses were being stopped. How? How do you stop such a big bus? How do you apply such a big force to stop a bus like that? All right. So these are the questions. These are the applications of Newton's observation. So Newton observed things, he wrote them down in the simplest of the mathematical form, and then applied it to different things, got applications out of it, and these applications of Newton's laws we call as mechanical engineering. All right. Yes. Boy of mass 58 kg jumps with the horizontal velocity of 3 meters per second. So what is the total initial momentum of the system? So when I talk about this scenario over here, I'll have to talk about the total momentum of the system before interaction. So you can see that the boy is interacting with the system, boy is interacting with the skateboard over there. All right. So before this interaction happened, what is the total momentum? So the total momentum of the system before interaction. All right. So I can say that the total momentum of the system before interaction. All right. The mass of the boy times the speed of the boy, which is, let's write it as UB, right? Mass of the boy plus into the speed of the boy, UB, that's the momentum of the boy plus the momentum of the skateboard, right? So this is the total momentum before the interaction happened. All right. So what is the total momentum of the system? Total momentum of the system after the interaction. So total momentum of the system after the interaction. All right. Now the boy is on the skateboard. There is no there are no 2 points over here. There is no boy and the skateboard. The system is one, the skateboard and the boy. So mass of the system now is mass of the boy plus the mass of the skateboard. All right, that's the system that we are in. So mass of the boy plus the mass of the skateboard into the velocity that we are asked to find. All right, so into the velocity, and this happens to be the final momentum. So let's look at what just happened over here. So the boy interacted with the skateboard, and boy and the skateboard are moving together. All right. So if that's the case, then what is the speed of the boy? What is the final speed of the boy and the skateboard? That's the question that they've asked. So now we can say that since there are no other forces, since there are no external forces acting, all right, in the horizontal direction, we are going to assume that there is no frictional force over here. All right. So there is no frictional force. Since there is no external force acting, I can say that the total momentum of the system is conserved. Total momentum of the system is conserved. Meaning, in the absence of any external forces. So why can I assume that there is no external force? Because first of all, there are the skating board has wheels. So even if there is a small friction, that because of the wheels, that frictional force would be reduced. So I can assume that there is no friction. And also, we assume that there is not much friction between the ground and the skating board in the first place. All right. So there is very small frictional force between the ground and the skateboard. And also, even if there is a small frictional, because the wheels are rotating, we can say we can neglect the frictional force over here. All right. So we are working under the assumption that there is no friction. All right. So total momentum of the system is conserved. So what does that mean? So the momentum does not change. So whatever the initial momentum was, final momentum would also be the same. Okay, so there is no new momentum coming into the picture unless there are external forces. So momentum cannot just come into the system if there are no external forces acting on the system. That's the simplest idea of Newton. So if the momentum of the system has to change, if the total momentum of the system has to change, then there must be some external agency to change that momentum. In the absence of such an external agency, the momentum of the system, rather the total momentum of the system, remains conserved. So mass, let me write down what is the initial momentum. Mass of the boy, which is 58 kg, into the initial velocity of the boy, which is 3 meter per second. All right, good thing that all of these quantities are in SI units, so I don't have to convert, plus the momentum of the skateboard, which is 0, and this is equal to the final momentum, which happens to be the mass of the boy plus the skateboard, which is 60, 58 plus 2, that is 60, into the velocity v. All right, velocity v is what we needed to find out, and let's see what it is. So velocity v is equal to 58 into 3 divided by 60, and I may simplify this further. So 58 by 20. So you can see that it is slightly less than 3. 60 by 20 would have been 3, isn't it? This is 58 by 20, so it is slightly smaller. All right, slightly smaller as we had expected. Yes, so v is equal to, this would come out to be 2.9 meter per second. So the final speed with the boy on the skateboard would be slightly smaller than the speed of the boy before he just jumped on the skateboard. All right, so this is an interesting problem, isn't it? So let's look at one more question over here. So a force acts for 0.1 second on a body of mass 1.2 kg initially at rest. So let's draw the picture over here. So yes, so this is my picture. So this is a body of 1.2 kg on which a force acts. They have not given the magnitude of this force. So let's say that the force is acting in this direction. Why not, right? So this force is F, and the force that is acting, say that the force acts in this direction, because why not? Why do we have to always say it acts in the horizontal direction or the vertical direction? Let's say it acts in that direction. It's just that we do not know what this force is. All right, but whatever this force is, it acts for 0.1 seconds. It acts for a very short duration of time. Okay, it acts for 0.1 seconds. The force then ceases to act. So this force is something like this. You can imagine that object over there, like a striker, carom striker, and you are exerting a force for a very short duration of time, like 0.1 seconds. All right, we are assuming that the force that we are exerting is constant force. All right, it's a constant force, and it acts for a very short duration of time. The force then ceases to act, and the body moves through a distance of 2 meters in the next 1 second. So the body has moved through a distance of 2 meters in the next 1 second. Find the magnitude of the force. All right, so let's see. So the body was over here, and the next second, what do I find? I find that the body has moved to a new location. Which is which is let's see, which is 2 meters from the initial location. All right, so what's happening over here? So the force acted only for 0.1 seconds, isn't it? The force acted for only 0.1 seconds. And let's revise what Newton's first law says. First law says that the body continues to stay at rest if it's initially at rest, and continues to move with uniform velocity if it was already moving with uniform velocity, until and unless acted upon by an external force. So the body would have continued to stay at rest if there was no force acting on that body. All right, so what happens when the force acts on the body? So the moment the force acts on the body, the state of motion of the body changes. So if it was at rest, it would accelerate during the application of the force. So imagine this: you have you and your friend are astronauts. You are in space, and you push your friend who is at rest. You push your friend with a force of certain magnitude, let's say. All right, you push your friend with the force of certain magnitude, and when you push your friend, he tends to accelerate, okay, for that short duration of time where you have applied the force. What happens later? Once you have stopped the push, the person does not keep on accelerating. No, he stops accelerating. Now, he was initially at rest, you pushed him, so it accelerated. He acquired a speed, he acquired an initial velocity, isn't it? Now he's going to continue to move with that in the same speed. His speed is not going to change. If there is nothing to stop him, then he would continue to move with that acquired speed. All right, so you push your friend, and he would continue to move with the same speed forever. All right, again, until when? Until and unless acted upon by another force. So if you act on your friend again with another force, maybe you could tie a thread and pull him like this, or anything, doesn't matter. All right, any sort of force that you apply on him, he would change his direction or the speed. Okay, he would change his velocity. All right, so for the small duration of 0.1 seconds, the body changes its velocity, but after that it continues to move with the constant velocity that it has acquired in that 0.1 seconds. All right, so let's see what happens over here. So they have told us that in the next 1 second, the body moves 2 meters, isn't it? So what must have been the final speed? What must have been the speed after the force stopped acting? So what is the speed? What is the speed acquired by the body? After the force ceases to act. Alright, so we can see that speed that the body acquired resulted in a motion of 2 meters in 1 second, isn't it? So whatever that force, speed is, we can obtain it by doing this displacement. And it's why can I simply divide displacement by time? Because this speed is a uniform speed, isn't it? Because no forces are acting here, so the speed is uniform velocity. This velocity is uniform. So 2 meters divided by 1 second, and that's the final speed acquired by the body after the force ceased to act. All right. So what does Newton's law say here? Newton's law says that, look at this now, that's the final speed. That's the speed after 0.1 seconds. So Newton's law would say that there is a change in momentum there's a change in momentum. Let me write that change in momentum as delta P. So what is the change in momentum? Change in momentum is the final momentum minus the initial momentum. That's the change in momentum. And what's the change in momentum? So final momentum is mass, which is 1.2 kg, into the final velocity, which is 2 meter per second, minus the initial momentum, which is 0, because it's been given in the question that the body was initially at rest. All right, body was initially at rest. So I can write that the initial momentum of the body is 0. So this is what the force does. It changes the momentum of the system. All right. So momentum of the system has been changed. And what is the force equal to? Force is equal to the change in momentum divided by the change in time. All right. So if the momentum changes quickly, if the momentum of the body changes quickly, then we say that a greater force is acting on the body. All right. That's how Newton defined his new quantity called force. If the momentum changes quickly, rapidly, then there must be a greater force acting on the body. If the momentum changes slowly, then there must be a smaller force acting on the body. All right. So Newton's definition of what a force is quite intuitive, isn't it? It's a quite natural definition to give to force, quite natural meaning to give to force, right? So delta P by delta T, let me write this down. So delta P is 1.2 into 2 divided by delta T. So delta T, let me just go back. So delta T is 0.1 seconds. So let me write that down over here, 0.1 seconds. Yes, so 1.2 into 2, that is 2.4 divided by 0.1 divided by 0.1. So that would be 24 Newton of force. All right. So 24 Newton of force must have acted on this body of 1.2 kgs for a small duration, 1 seconds, so as to acquire, so that the body can acquire a speed of 2 meter per second. All right. So that's the problem. So let's look at one more problem. There seems like a lot of problems that I work out, isn't it? So solving problems is one of the most important aspects in physics. Okay, one is discovering principles. You discover new things about nature, and then solving problems. So one interesting story is about Lord Kelvin. So Lord Kelvin was a very good mathematician. All right. So when Charles Darwin put forward his theory of evolution, all right. So when Charles Darwin put forward his theory of evolution, Charles Darwin required that the Earth be billions of years old. Otherwise, there wouldn't be sufficient time for the process of evolution to take place. All right. And Lord Kelvin, being a clever mathematician and a clever physicist, told that it is impossible that the Earth is a billion years old. All right. Do you know what was his justification? He calculated that if the sun, and there is something called as gravitational energy, all right. So based on the gravitational self energy of the sun, he calculated that if only gravity for the sun is responsible for the energy output of the sun, then that sun cannot be more than 20 million years old. All right, cannot be more than 20 million years old. And if the sun itself is not more than 20 million years old, then Earth cannot possibly be billions of years old. All right. Now, why do I say he's clever? Because you know that Earth is definitely a billion, more than 4.6 billion years old, isn't it? Lord Kelvin was definitely wrong. But why was he wrong? Because he did not know that the energy that we get from the sun is not due to gravitational self-energy, but something called as nuclear fusion that happens in the sun. All right. And he did not know that. All right. See, that's the knowledge part. That's the knowledge part of physics. You discover things about nature and then you apply it. So Lord Kelvin only understood about gravity, how gravity works. And based on that information, based on that knowledge, whatever calculations that he made were perfect. All right. It's just that he did not know, and he could not possibly have known that the energy of the sun, energy that is coming out from stars, is not because of gravitational self energy, but because of fusion, which we know now. All right. And based on the calculations that we get from based on the calculation that we get from the fusion reactions, we can safely say that the sun and the earth are billions of years old. Look at this. How do we say things like this? With confidence. We say that with confidence that earth is a billion years old. Okay? Because we have looked around, we have looked at the fossils, we know things, and the data that we get from the fossils and data that we get from the solar energy and all of those things tally with each other. It's not like one data gives you one information and the other data gives you another information. No, all of these things, even though they are separate concepts, you'll find that there is some sort of tally between these different concepts. All right, that's why I keep saying that one aspect of physics, one aspect of all sciences, is to gather information, is to do observations and get the principles that are governing the nature. I was saying one aspect of one aspect of all sciences is to discover principles that govern the nature, and the other one is to do calculations like this. So if you just gather information and not solve problems, okay, if you are not skilled enough to solve problems, you might not see the link between the natural laws and certain interesting facts. All right, like the age of the universe. That's a calculation based on other observations that we have made. Have you ever wondered how they calculated? How 2,000 years back, about 2,000 years back, somebody calculated the radius of the earth, right? He calculated the radius of the earth. Just imagine that. And it was pretty accurate. It was not very off. It was off, but it was not very off. And that is something that is amazing, how you can calculate that the radius of earth is so and so. All right, like mass of the earth is 5.4 into 10 power 24 kg. How do you calculate that? Mass of the sun is 10 power 30 kg. How do you calculate these things? So this is what we do in physics. We calculate, we understand nature, and we see things differently. All right, so do not think that these problems are just problems and which can score you marks in the exam. That is certainly one aspect of it, right? But the other aspect of it is to train you to look at nature differently, to calculate things for yourself. All right, so even though these problems might seem like they are only to do with the your exam point of view, they are not really that. All right, there is certainly a part of it that has to do with the exams. Of course, I'm not denying that. I, as a student, did do the problems for the sake of the exams, but that's me. But I do encourage you to do these problems so that they could be a guide to you into the laws of nature, the workings of the nature. All right. Yes. So a motor car is moving with a velocity of 108 km per hour, and it takes 4 seconds to stop after the brakes are applied. Calculate the force exerted by the brakes on the motor car if its mass along with the passengers is 1000 kg. Now this is a straightforward problem, right? So a motor car is moving with a velocity of 108 km per hour. Now the problem is the mix of units over here. So you can see that the velocity is given in kilometer per hour, and the time it takes to stop the vehicle is given in seconds, and the mass is given in kg, which seems to be an SI unit. So we want all the units to be in the same system of units. All right, we do not want any confusion. Of course, why do I insist such a thing? Because if I asked you to measure the length of a certain object and you measure the length in parts, let's say you measure the length of the rod AC and you measure it in parts, you said, okay, this was 2 meter and this length here was 4 feet, so the total length is 6 feet or 6 meter. That does not make sense. So when you're adding things, adding quantities or multiplying quantities, you make sure that they are of the same kind, right? Since I'm doing these problems, of course this isn't same as adding lengths, but force in newtons is a SI unit. It is defined as 1 kg mass moving, the force that you require to accelerate a 1 kg mass at the rate of 1 meter per second, right? So the definition of the force, Newton force, a force of Newton, is given in SI. So we'd want all the things to be in SI so that the answers make sense. All right. So the step number 1 would be to convert the speed 108 km per hour into SI unit, which is meter per second. So 108 into 5 by 18, that would be the conversion factor, isn't it? So conversion multiplied by the conversion factor. So this would be the speed in meter per second. All right, I'm not going to do the I'm sure there is a way to simplify this, 108 and 18, right? So let's keep it as it and see what happens later. All right, so motor car which is moving with this speed is brought to a stop in 4 seconds. So calculate the force. Again, the strategy would be the same thing, right? So the mass of the car along with the passengers happens to be 1000 kgs, right? So the momentum of the car before the brakes are applied happens to be 1000 into the velocity. Momentum is mass into velocity. So mass, which is 1000, into the velocity, which is 108 into 5 divided by 18. That's the momentum of the car initially, right? Final momentum would be 0 because the car is brought to rest. Mass is still 1000 kgs, but the velocity is 0. So final momentum is 0. And you can see that the time it took for the car to be brought to rest is 4 seconds, right? So what is the force? Now the force need not be a constant over here, right? So when you apply the brakes, the force need not be constant. So let's say that we are calculating the average force. Average force is the total change in momentum divided by the total time taken. Averages are always defined like that. If you recall my lectures on average velocity, total change in distance divided by total change in time. Oh, I'm sorry, I said average velocity. So total change in displacement divided by total change in time. Here average force would be total change in momentum divided by total change in time. So what is the total change in momentum? So the total change in momentum I may write as Pf minus Pi divided by the total change in time, which is 4 seconds. So Pf is 0 minus Pi, so that is 1000 into 108 into 5 divided by 18, the whole divided by 4. Now I get that the average force is equal to minus 1000 into 108 into 5 divided by 4 into 18. Now the reason why I did not simplify this in the beginning is that I thought maybe later there would be some nice factors, some nice numbers that would cancel each other out, and I wouldn't have to bother doing it. But it turns out that I'm forced to do this division now. So let's go ahead and do it. So 18 and 108. Now how do I think about this? Now I know that if there were 10 18s, then I would have a 180. If there are 10 18s, then I would have a 180. So if I had half the number of 18s, that is 5, I would have had 90, right? So this number 108 seems to be 18 more than 90. Look at that, 18 more than 90. So how many 18s do I have? So I'd have 6 18s, right? So this goes once and this goes 6 times. All right. Of course, I do these things because I forget the multiplication table. All right. Excuse me. I'm getting old. I do not remember the multiplication table, so I'll have to do this. So if you remember the multiplication table, you can go ahead and do it. All right. So 1000. So this goes once and this goes 250 times. Okay. Now all that remains to do is to multiply these things out. So minus 250 into 6, minus 250 into 6 would be, let's see, that would be a 1500, isn't it? 250 into 6 would be 1500. So 1500 into 5, 1500 into 5, that would be 7500. So the average force is negative, meaning it's a retarding force, which means that it stops the car, isn't it? It's in the opposite direction, and its value is negative 7500 Newton. All right. So that's the magnitude of the force that is required to stop a car that is 1000 kgs along with the passenger in 4 seconds. All right. Now, like I've told you, that it's not possible for the person sitting inside the car to apply such a big force, 7500. I hope you understand how big this force is. In case you do not understand how big this force is, let me give you an idea as to how big the size of the force is. 7500 Newton. Now suppose you weigh 75 kgs. Why I choose 75? Because of the obvious reason. There is 7,500 there. Suppose you weigh 75 kgs. All right. So the force that you would be exerting on the ground, so this is you. So this is you. The force that you're exerting on the ground would be 750 Newton. 750 Newton. All right. So that's the force that you exert on the ground. So let's say you hold in your hands a bar. A bar like that. Okay. So what is this 7500 Newton of force? How much should be the weight of the bar? Mass of the bar, sorry. Or how much should be the mass of the bar such that you exert 7500 Newton? Can you guess how much should be that? So you already, if you're 75 kgs, you would exert a force of 750 Newton. If the total mass of your body along with the bar is 750 kgs, then the force that you would be exerting on the ground would be 7500 Newton. All right, then the weight would be 7500 Newton. So how much should this be? This should be 650 kgs. So 650 kgs, no human being is capable of holding 650 kgs. I know you might see some strongman competitions on YouTube, but I don't think they can hold 650 kgs, even though they are the biggest and the baddest of the human beings. They cannot hold 650 kgs for more than a second. I do not think so, right? So 650 kg of weight would have to be pressed by the person on the brakes, right? That much of force. But do we do that? Anybody can press the brakes, isn't it? You do not require to be a strong man, certainly, to stop a car. So I encourage you to go through some material on the internet or somewhere, look into some books and figure out why and how is this working. All right. Yes. A force of 20 Newton acts on a body of mass 5 kg for 5 seconds. All right. Find the acceleration of the body, velocity at the end of 5 seconds, displacement at the end of 5 seconds. All right. So let's see what's happening over here. So we have a body of mass 5 kg. We have a body of mass 5 kg. And a force, a constant force of 20 Newton acts on this body. A constant force of 20 Newton acts on this body for 5 seconds. So for 5 seconds. All right. So it's not like you just push the body and leave it. You know what would happen in that case. So we have done the problem before this, where we push the body once and left it. So body would acquire a speed and continue to move with that speed forever, right? So here we keep on pushing the body with a constant force of 20 Newton for 5 seconds. Okay. So what we would have is a constant acceleration. So if the body is initially at rest, it would acquire speed, and that speed would continuously change for 5 seconds. All right. So that's what acceleration means, isn't it? For 5 seconds, the speed keeps on changing. So let's find out what that change in speed is. All right. Or the change in rate of change of speed is. So rate of change of speed, which we call as acceleration, and Newton's law says that acceleration. So where do I get this law from? Let me not give you anything new information. So Newton's law says that the force is equal to rate of change of momentum with respect to time. All right. So now the force is constant. Remember, force is a constant. The force is a constant. Let's see what that means. So dp by dt is constant. Delta p by delta t is a constant. Delta p by delta t is constant because why? Because that's equal to force, and force is constant, isn't it? So what is delta p by delta t? So delta p by delta t, let me expand delta p out. So delta p is mass into velocity, this is the final momentum, minus the initial momentum, divided by delta t. The time interval that the body requires to change the momentum from mu to mv. So mass is a constant over here, so I can take that mass out. So what I'll find is that v minus u divided by delta t into mass is equal to the force. So v minus u divided by delta t. Right? Now, if the force is constant, then I've told you that delta p by delta t is a constant, and therefore this quantity over here, mass is anyway a constant. See, this is a constant. Understand what I'm trying to say? This is a constant. Mass does not change. We are assuming in this case mass does not change, and in most of the cases mass does not change. So mass is a constant, right? So force is a constant given in the problem. So constant is equal to constant times constant, isn't it? This quantity over here also has to be a constant. Otherwise, it would not work out. So constant times a variable will not be a constant, right? Constant times a constant is a constant. So this quantity over here must also be a constant. So what is this quantity here? So v minus u divided by delta t. V minus u divided by delta t, and that is the acceleration of the body, isn't it? That's the definition of the acceleration of the body. V minus u, when acceleration is constant, then it is v minus u divided by t. That's the first kinematic equation that you see there for constant accelerations, isn't it? Yes. So we have F is equal to mass times acceleration. So F is equal to mass times acceleration. Yeah. So let's see. So we get a new equation from the old one, which said that the force is equal to rate of change of momentum. Now I say that the force is equal to mass times acceleration, right? So let's see. So 20 Newton of force acts on a body of 5 kg for 5 seconds. So what is the acceleration of the body? Now the acceleration of the body is constant because the force is constant. So acceleration of the body is from Newton's new law that we have written down. Acceleration is equal to force by mass. So force is equal to 20 divided by the mass of the object, which is 5 kgs. So the acceleration, which is a constant value, comes out to be 4 meter per second per second. So acceleration is 4 meter per second per second. That is the rate at which the velocity is changing every second. So in the first second, what would be the change in speed? So body starts from rest. So in the first second, the speed would change to 4 meter per second. In the next second, it would change again by 4 meter per second, and this would continue for 5 seconds. So we have found the acceleration. What is the velocity at the end of 5 seconds? So I can use this expression over here, isn't it? So we know that acceleration is equal to v minus u divided by delta t. So I want v. What is v? The velocity at the end of the 5 seconds. So let me just rearrange this equation. So v is equal to u plus a into delta t. Okay, so u is equal to 0. We are starting with 0 speed, and the acceleration, the rate at which the speed is changing is 4 meter per second every second. So 4 meter per second every second, that's the change in speed, into the time taken, which is 5 seconds. So the speed of the body at the end of 5 seconds is 20 meter per second. That's the second part of the question. Okay, what about the third part of the question? Third part of the question asks for displacement at the end of 5 seconds. So since the acceleration is constant, I can apply the kinematic equation. Let me apply the third kinematic equation. I know that you're thinking we could apply the second kinematic equation just to have some change in the way we do problems. Let me use the third kinematic equation, which says that v square is equal to u square plus 2 into a into s. Alright, so s is what I need. Displacement is what I need. I know v square. V square I just found out. Right? I found out v, but I can find v square. So s is equal to v square minus u square divided by 2a. Right? So v square is equal to 20 square, which happens to be 400, minus u square, which is 0, divided by 2a, 2 into 4. So this would come out to be, let's see, 400 by 4 is 100, 100 by 2 would be 50 meter. So the displacement of the object would be 50 meter in 5 seconds under the action of a constant force 20 Newton on a body of 5 kg in a time of 5 seconds. Yes. So that's the end of the problem. Alright. So what we learn over here is that if I tell you the mass of the object and the force acting on the object, if I tell you the mass of the object and the force of the force acting on the object, in principle you'll be able to tell me everything about the object, like what is its displacement in 5 seconds, what is its velocity in 5 seconds, what is its acceleration, right? You can do all these things provided you know the force acting on the body and mass of the body. So everything else can be figured out, all right, provided you are clever enough, right? Yes. So that's the end of the problems.